Hi, Math 31s. This lesson is going to be on the limit of trig functions, and specifically we're going to be looking at the limit of sine of x and the limit of cos of x. Before we start, though, looking at the limit of trig functions, I want to talk about a couple identities that you need to know from Math 30-1. So the first identity that you need to know and memorize from 30-1 was the Pythagorean identity sine squared of x plus cos squared of x. And remember, whenever you see sine squared of x plus cos squared of x, the answer is equal to 1. That's the identity. So, for example, if in our practice problems later on, let's say we see 1 minus cos squared of x, and that's going to be maybe a factor that we'll see, we can take out 1 minus cos squared of x and input its identity. So the identity for 1 minus cos squared of x would be sine squared of x. Right? Because if I said subtract cos squared of x from both sides, you'd have 1 minus cos squared of x is equal to sine squared of x. So just substituting out the identity. The other identity that you need to know is the double angle identity for sine. So the double angle identity for sine, remember when we have an angle or the argument that's been doubled, that would be a double angle. So sine of 2x is equal to 2 sine of x cos of x. We'll encounter this in our note package and in the homework as well. Okay, so let's look at the limit of sine of x and the limit of cos of x graphically. So here's the graph for y is equal to sine of x. This graph, remember, sine of x starts at the origin and it goes into its rise. Its period is 2 pi, and it has a max value of 1 and a minimum value of -1. What we're going to answer is the limit as x approaches 0 of sine of x. So remember, in order for a limit to exist, left-hand limit must equal right-hand limit. So as I approach 0 from the left, and as I approach 0 from the right-hand side, my function is approaching 0. So we would say that the limit as x approaches 0 of sine of x is equal to 0. Remember, we're also able to directly substitute in. So if I wanted to, I could write the limit as x approaches 0 of sine of x is equal to the sine of 0. And the sine of 0 from our unit circle, so whether it's 0 degrees or 0 radians, this would be the sine of 0 right there. And my coordinate is 1 comma 0. Remember that your x coordinate on your unit circle would be your cosines and your y coordinate is your sines. So the sine of 0 degrees or 0 radians is simply 0. If we were looking at the cosine graph, our cosine graph, it starts at its peak. So it starts at 1 and it goes into a fall. If we were answering the limit as x approaches 0 of the cosine of x, so as I approach my limit from the left and as I approach my limit from the right-hand side, my function is approaching 1. So graphically, the limit as x approaches 0 of cos of x is equal to 1. If I was to substitute in, the cosine of 0 degrees or 0 radians is equal to, cosine is our x values on our unit circle, it's equal to 1. Okay, what's going to happen when we do the limits of trig functions is we're going to get 0 over 0. We're going to be indeterminate for many, many cases. And remember from the beginning of limits, if we are indeterminate, we have to do a few things so that something will cancel and will no longer be indeterminate. So with trig, we'll be factoring, rationalizing, simplifying. Multiplying by the conjugate is going to be a big one in trig. And then another one that we have to think of now for trig is we have to think of our identities. So we might need to swap out with a Pythagorean identity so that we're able to factor. And then from there, we could cancel so that will no longer be indeterminate. Okay, let's look at the limit as x approaches 0 of sine of x over x. So first of all, if we were to graph this, the limit as x approaches 0 of sine of x over x, we know that there's a non-permissible value and x cannot be equal to 0. What this would look like graphically is graphically at 0, I would have a hole. The graph is going to look something like this. So what happened? And the whole is at 1. So as I approach graphically from the left, as I approach from the right, I'm going to get an answer when we have sine of x over x. I'm going to get, my limit is going to be approaching 1. We could look at this also numerically. So remember, if you were to type in on your calculator sine of 0 over 0, sine of 0 is 0, we're going to be indeterminate, right? Will be 0 over 0. But we could approach from the left side of 0. So if we approach, and if we're going to look at this numerically, so if our x values approaches 0 from the left-hand side, what our function is going to approach is going to be 1 on our calculator. So f of x will approach 1. And then remember, we could approach 0 from the right-hand side. So this would be nice and close to 0. As our x values approach 0 from the right-hand side, our function is going to approach 1. So this is just numerically showing how the limit as x approaches 0 of sine of x over x is going to be equal to 1. Okay? What's going to happen is we're going to look for this case all the time. When we see sine of x over x, we're going to substitute that out and we're going to put in a 1. As well, one thing I just want to note is let's say we see the limit as x approaches 0 of sine of 5x over 5x. So this argument is the same as this term down here. This argument is the same as this term. If we see this, that limit is going to be equal to 1. Okay? Or it could be sine of 7x over 7x. If we see that case, we're going to substitute out and put in a 1. Let's look at number 4, which is the limit as x approaches 0 of x over sine of x. So it's what we were just looking at, except we have, it's reverse, it's reciprocated. X is on top, sine of x is on the bottom. This would give us indeterminate. We'd have 0 over the sine of 0. We'd have 0 over 0. So graphically, I'm going to show you what this would look like. You don't need to memorize the graph. You just have to memorize the case. So what's going to happen graphically is we would have a couple of asymptotes in our graph. And over here at 1, our graph's going to look like this. And then we'd have something happening down here, something happening down here. But as I approach 0, on the left and right-hand side, my limit will be approaching 1. So again, whether we see x over sine of x, or if we see sine of x over x, we're going to take that out and we're going to put in 1. Okay, so let's start getting into this and see what these questions are going to look like. So let's look at this guy. The limit as x approaches 0 of 1 minus cos of x over x. Cos of 0, cos of 0 is 1. So I'd have, if I put cos of 0 here, I'd have 1 minus 1, so I'd have 0 over 0 indeterminate. So what do we do if we're indeterminate? We either factor, we rationalize, or we multiply it by the conjugate. So we're going to be multiplying by the conjugate. And our conjugate is going to be, the conjugate of 1 minus cos of x is going to be 1 plus the cos of x. And remember what you do to the bottom, or sorry, what I do my numerator, I have to do to my denominator. This is equal to, so the limit as x approaches 0, remember just expand your conjugate. 1 times 1 is 1. Negative times positive will be negative, and it's going to be cos squared of x all over x times 1 plus cos of x. Remember, don't expand unless you must. So I only expand the conjugate. I'm not going to expand down here because I'm hoping something's going to cancel. Okay, I do not want to do a difference of squares because if I do a difference of squares up here, I'm going to be back to where I started, right? So I don't want to do that. So this is where an identity will come into place, and we're going to have a Pythagorean's identity. So the identity that hopefully you see is sine squared of x plus cos squared of x is equal to 1. So 1 minus cos squared of x, I'm going to replace that, if I subtract cosquared of x from each side, I'm going to be left with the identity, which is sine squared of x. So this is equal to the limit as x approaches 0 of sine squared of x over x and then 1 plus cos of x. Okay, I'm going to rewrite my numerator to look as follows. So sine squared of x, so the limit as x approaches 0, that's really the sine of x times the sine of x all over x, and then we had 1 plus cos of x. What we are going to be looking for when we're doing trig limits is we're always going to be looking for that case sine of x over x or x over sine of x. Because if ever I see this, this is going to be equal to 1. So this is equal to the limit as x approaches 0, that's really 1 times sine of x over 1 plus cosine of x. Okay, so now that I was able to not cancel, but I was able to use my this case because we know that that's 1. Now I could substitute in 0 here. So what I'm going to have is I'm going to have the sine of 0 all over 1 plus cosine of 0. Now, the sine of 0, and I should bring out, I had a 1 here. So it's 1 times sine of 0 is 0. 1 plus cos of 0, cosine at 0 is 1. So this is going to be equal to 1 times 0 over 2. 1 times 0 is 0. So it's a lot of work just to get 0 as an answer, but this you'd be marked on your work, okay, and not just getting 0. Let's look at number 6, which is going to be very similar to number 5. So again, if we were to plug in 0, we would get 0 over 0 indeterminate. So then you say, what do I do? Can I factor? Can I use an identity? Can I do the conjugate? This would be a conjugate. There's no identity right now. There's no factoring right now. So we'll do the conjugate. So the conjugate is cos of x plus 1 all over cos of x plus 1. This is equal to the limit as x approaches 0. You could expand out your conjugate. Cos of x times cos of x is cos squared of x minus 1 all over x times cos of x plus 1. Okay, so again, the purpose of doing the conjugate was now we're going to use our Pythagorean identity. So sine squared of x plus cos squared of x is equal to 1. Now be careful here. The identity that I want to replace is cos squared of x minus 1. So cos squared of x needs to be positive. I need to bring the 1 to the left-hand side. The identity for cos squared of x minus 1, I'd bring sine to the right-hand side. So it would be negative sine squared of x. So this is equal to the limit as x approaches 0 of negative sine squared of x all over x cos of x plus 1. Okay, what I'm going to do, and I actually could have done this up here. Remember from our properties of limits, the limit of a constant is the constant. So what I could have done to this one is I could have actually just brought that in front. So this negative is going to be my constant. I'm just going to bring that to the front. And I'm going to rewrite this as negative 1 times the limit as x approaches 0. Let's rewrite sine squared of x as sine of x over sine of x. Sorry, sine of x times sine of x. All over x, and then we had cosine of x plus 1. We will always want to look for this case. Okay, so that case is going to make sine of x over x is going to be 1. So I had negative 1 times the limit as x approaches 0. This is going to give me a 1. And then I had the sine of x over the cos of x plus 1. Okay, so now let's substitute in. I had negative 1, 1, sine of 0. Okay, so if I plug in the sine of 0, and then cos of 0 plus 1. So negative 1 times 1. Sine at 0 is 0 over 1 plus 1 is 2. So again, I still get 0 here, but I needed to go through and show all of this work to allow me to get 0. Okay, class example number 7. What I want you to see with this 2, and there's in front of my coefficient of the sine of x is 1, I'm going to rewrite this to look as follows. The limit as x approaches 0 of 1/2 times, so I just want you to see that that's the coefficient, the sine of x over x. According to my properties of limits, the limit of a constant is the constant. So let's bring that 1/2 in front. So it's 1/2 times the limit as x approaches 0 of sine of x over x. There is my case that I always look for, sine of x over x, or I want to look for x over sine of x, but that's 1. So it's going to be equal to 1/2 times 1. This limit will approach 1/2. Okay, this guy right here. I'm going to show you 2 different ways how we could solve this limit. So the first way, again, we'd get 0 over 0 would be indeterminate, because if you put 0 in here, I'd get the sine of 0, which is 0 over 0. So first thing you could look at is you could say, oh, this is that was the double angle for sine identity, right? So I could rewrite this as the limit as x approaches 0 of sine of x, or sorry, double angle for sine is 2 sine of x cos of x all over x. Okay, the limit of a constant is the constant. And I'd have sine of x cos of x all over x. There is the case that I'm looking for. So I would have 2 times 1 times the cosine at 0. And cosine of 0 degrees, we know that that answer is 1. So it's 2 times 1 times 1. So this answer is 2. Okay, I'm going to show you a second method that we could solve this question. And this is for if you did not see that it was a double angle for sine. And we're going to do this strategy a lot in the next couple examples. So the limit as x approaches 0 of the sine of 2x over x. From the beginning, when I was showing you the limits, I had told you that if we're able to get to the sine of 5x over 5x, it would be equal to 1, or sine of 7x over 7x. As long as we can see that case, it's going to be equal to 1. So what I have, if you didn't see that it was a double angle for sine, there's an alternate strategy you could do. You could say to yourself, okay, if this is sine of 2x over 2x, that is the case that we're looking for, and it would become a 1. So what I mean by that is if I add a 2 here, right now this is going to equal to 1. However, I can't just add a 2 in my denominator. If I add a 2 in my denominator, I have to balance it by putting a 2 in my numerator. Okay? What happens here is I'm just going to rewrite this as the limit as x approaches 0. This is 2 times the sine of 2x, or the double angle of sine, so I'm just going to put that 2 in front. And then I have the sine of 2x over 2x. The limit of a constant is the constant. again, if you see this case, we know that that's 1. So I'm going to have 2 times 1, which is 2, which is the same as we got above using an identity. I'm going to show you another one um, exactly like this one with using this strategy. Okay, number 9. The limit as x approaches 0 of sine of 7x over sine of 4x. We're going to be indeterminate. What I want you to do is I want you to split this up to look as follows. The limit as x approaches 0. So my numerator was the sine of 7x. I just want you to write it like that, times my denominator had the sine of 4x. Okay, so why am I separating it? Well, I'm always looking for the case sine of x over x or sine of 7x over 7x. So if I introduce a 7x down here, I like this because this becomes that case and that limit's going to be equal to 1. But you can't just introduce a 7x in the denominator. If you do that, you have to balance it out by having a 7x in the numerator. So if I'm going to put a 7x down here, I need to put a 7x up here. Over here, it's going to be the same thing. Remember, if you see x over sine of x, or 5x over sine of 5x, if you see that, the limit as x approaches 0 is also 1. That case is also equal to 1. So over here, I have 4x in the denominator. If I can put 4x up here, this will give me the 1, but I have to balance. If I put 4x in the numerator, I need to put 4x in the denominator. Okay, so what's happening is this is going to approach 1. This is going to approach 1. X over x will cancel, and we'll be left with 7 over 4. This limit is going to be equal to 7 over 4. There's going to be a few of these in the homework, so what I will do is I'm going to have a second video of me solving some homework questions, and I'm going to do this strategy where I'm going to separate, and then I'm going to try to always create the case of sine of 7x over 7x. Okay, this one here, we are not approaching 0, so we don't need to worry about potentially being indeterminate. We could always try, remember, just direct substitution. So for this one, if I input pi over 4, I'm going to have the tan at pi over 4 over 4 input for x pi over 4. In my denominator, 4 over 4 will cancel, and I'll be left with pi in my denominator. Now, from your unit circle, you have to know what tan at pi over 4 is. Remember that tan is y divided by x, so it's root 2 over 2 times the inverse of this, but tan at pi over 4 is 1. And that would be your answer. Okay, this one here, we would be indeterminate. If you typed in, if you substituted in tan of 0 over 4 times 0, we know we're going to get 0 in the denominator. Tan of 0, remember it's y divided by x, so it'd be 0 divided by 1, which is 0. So tan of 0 is 0. So that's indeterminate. Okay, so how are we going to do, what do we do if we have indeterminate and we've got tans? We're going to have the limit as x approaches 0. We know that the tan of x is the sine of x over the cosine of x, all over 4x over 1. This is equal to the limit as x approaches 0 of sine of x over cos of x. We're going to multiply by the reciprocal, which would be 1 over 4x. Okay, let's rewrite this so you could see it a bit better. The limit as x approaches 0, I have sine of x in my numerator. In my denominator, I have a 4, I have an x, and I have a cosine of x. 1 over 4 is a constant. I'm going to get rid of that. Here is the case that we're always trying to make, sine of x over x. And then it doesn't matter if cosine is in the denominator because cos of 0, when I input 0, cos of 0 is simply 1. So what would we have? We would have 1/4 times the limit as x approaches 0, sine of x over x times 1 over cos of x. That's equal to 1/4. That's equal to 1. 1 over cosine of 0. Cosine of 0 is 1. So 1/4 times 1 times 1, sorry, this would be 1 over 1. So 1/4 times 1 times 1 is just 1 over 4 would be my answer. Okay, let's do a couple more with simple identities that we could take out. Oh, no. Okay, let's look at this one. We would be indeterminate because I get 0 in the denominator and 1 minus cos of 0, 1 minus 1 is 0 over 0. So you say, what do? We can't factor. We're going to multiply by the conjugate. So let's multiply by the conjugate, see what we get. We're going to have the limit as x approaches 0. Expand your conjugate always. So 1 minus cos squared of x all over. Don't expand your don't expand the non-conjugate. Just keep those in factored form. Okay, so let's look at that numerator. Hopefully you're going to see the Pythagorean identity. And it's 1 minus cos squared of x. So the identity for this would be sine squared of x. My denominator, I had a 2x squared, and then I had 1 plus cos of x. Okay, so if you could pull out constants, pull out constants. So that's going to be pulled out. Then I have the limit as x approaches 0. And I want you to see this sine squared of x. Sine squared of x is really sine of x times sine of x. My denominator has x squared. We know that x squared is just x times x. So if you could see, I've made those cases. And then I've got 1 plus cos of x in my denominator. Okay, this is equal to 1. This is equal to 1. So what I have is 1/2 times 1 times 1 times 1 over 1 plus cos of 0. 1/2 times 1 times 1 is 1/2. Cos of 0 is 1. So 1 plus 1 is 2. This answer is also 1 over 4. We'll look at 2 extra examples, and then you will practice your homework for this. Okay, so let's look at this. Limit as x approaches 0, and say, what can I do? I'm going to be indeterminate. You don't even need to check, but what will I need to do? So tan, actually, let's get rid of this 2 to start with. Might as well do that. So pull out your constant. Limit of a constant is the constant. And we know the identity for tan, right? Tan is sine of x over cos of x over, I have an x, and then secant, you guys, is 1 over cos of x. So what I really have in the denominator is x over cos of x. Maybe I'll switch that. Okay, let's rewrite this. Instead of dividing, let's just multiply it by the reciprocal. Or you could do your complex fraction and multiply top and bottom by cos of x. But I'm just going to rewrite it by multiplying by the reciprocal. So I've got sine of x over cos of x times the reciprocal of this would be cos of x over x. Cos of x and cos of x will cancel. And look what I'm left with. Sine of x over x. Whenever we see that, we know that that's 1. And I get 2 as an answer. Let's look at 14, our last question. So again, nothing could factor from here, right? I don't have any squareds, nothing can be factored, there's no identities, no Pythagorean identities. So let's take out, let's replace tan of x with the identity for tan of x, which is sine of x over cos of x. So I'm going to have the limit as x approaches 0 of sine of x over cos of x minus sine of x all over x cos of x. Okay, I could do common denominators here and then multiply by the reciprocal, but you know what I'm going to do? Let's do this as a complex fraction. And let's say, what would we multiply this numerator by to get rid of that cos of x? So I would multiply my numerator by cos of x, and what you do to the top, make sure you do to the bottom to balance it. This is going to give me the limit as x approaches 0. When I distribute in that cos of x, I'm going to have cos of x over cos of x will cancel, and I'll be left with sine of x. And then I'm going to have minus cos of x times sine of x. In my denominator, I'm going to have x, and I'm going to have 2 cosines of x. So cos squared of x. Okay, so what I want you to look at here is in my numerator, what would happen is hopefully you could see that we could factor out a sine of x. So I'd have the limit as x approaches 0, factor out of sine of x, and you would have 1 minus cosine of x all over x cos squared of x. This is the case that we are looking for, which is going to give me a 1. 1 minus cos of 0. Okay, sorry, 1 minus cos of 0. Cos of 0 is 1. So 1 minus 1 will give me 0 over, in my denominator, cos of 0 squared. So cosine of 0 is 1. And if I square that, I get 1. 1 times 0 is 0. Okay? This definitely needs to be practiced. So you will be really good at trig limits, because what you're going to notice is you're going to see the same things over and over again. You're going to know when to do conjugate, you're going to know when to factor, and you're going to know when to see that case sine of x over x or x over sine of x is going to be 1. But it just needs practice. So here are your homework questions. Like I said, I'm going to upload a video that will have me solving on the video a lot of these homework questions. And you could watch the video, or you could work with a partner. Is often really good to do this homework so that you could say to each other, like, okay, here's that case, or this is what you would be doing. Okay, so good luck with that homework.